I would like to introduce Anthony. Hi, Anthony.
Hello, everybody.
I will give you mic to you.
Okay. All right. Thank you. Okay. Can you see the screen? Okay. Okay, great. Thank you. All right, so my name is Anthony. I work at Microsoft, and also I work on lots of Python projects. My website is here at tonybaloney.github.io. I have a blog on there, as well as some of the GitHub projects that I'm involved with. I'm also on Twitter at Anthony PJ Shaw, and I'm on Mastodon at tonybaloney@fostodon.org. So we're here today to talk about performance in Python. And we're going to do that in two areas: microanalysis, which is the analysis of small things. So that is zooming in and doing optimizations on small pieces of code. And we're also going to look at macroanalysis, which is looking at the whole system or the whole application. A big focus of my talk is going to be on benchmarking and measurement of performance. And first of all, we're just going to have a look as an overview of performance. This talk I recommend you watch. It's from PyCon 2021. It's by somebody called James Murphy, and it's a really interesting talk. If you look for this title in YouTube, it's available on YouTube. And the speaker shows how they made a NES emulator in Python. And it's an interesting talk if you're a Python developer, because they tried to write a NES emulator in Python, and it ran at 3 frames per second. So it couldn't run a Mario, the original Mario game from 1980, which is what, 40 years old, I think, the game. A modern computer couldn't run that in Python. They did manage to get that running efficiently by rewriting everything in Python. I made a fork of their original emulator, and without using Python, just using pure Python, made it about 6 times faster. So you could just about play Mario, but you did need quite a lot of compilation. So that measure is quite extreme. And when it comes to Python code, when you want to make the code faster, I think you've got 2 ways of looking at your options. There's how much impact you want to have, like how much faster you want the code to be, and how many changes to your code you're willing to make. So the most extreme one, I think, is to rewrite in Rust or Python or C++. This is a pretty extreme measure. It's the most performant way of running code or modules, but it is the most drastic. And then I'd say you've got the minimum number of code changes, but the biggest impact is to simply have more servers or more CPUs. So if you don't want to change the code at all, you can just run it on more infrastructure. And then we've got lots of other options somewhere in the middle. PyPy is another option, which works in some cases, but is often not compatible with many types of extension modules for Python. 2 areas that I think are particularly important is to optimize the database, to optimize I/O, and to introduce caching. These things do require code changes, but not as much as a rewrite, and the impact can still be significant. Then you've got things like minor version Python upgrades. Upgrading to the latest version of Python can often have a code performance improvement without necessarily needing to change the code. And then lastly, I think you can optimize your existing code and look at your algorithms in the implementation. You can also parallelize code where appropriate. So these are some techniques and some ways of looking at the problem. So microanalysis is the first part. So if you want to look at optimizing a block of code, there's some things that I suggest that you do and things that I suggest you don't do. First of all, you absolutely need to measure before you make changes. So before you try and optimize a piece of code, you need to measure how fast it runs at the moment. The reason you do this is because you need to measure whether you're making improvements or you're actually making the problem worse. You need to vary your inputs, and we'll talk about that in this talk. And you need to isolate your changes. So when you're doing micro optimizations, don't make too many changes at once. Try to change one thing at a time and to run a benchmark every time you make a change. And another thing with micro optimization is that it's very hard to measure small changes. So often what you want to do is to run a loop and run the same block of code thousands, if not millions of times in order to reduce the noise and see what the impact is. I'd also strongly advise that you don't assume the impact will be the same across Python versions. So if you're benchmarking on Python 3.8, then that benchmark might not have the same change in Python 3.10 or 3.11. And don't make changes if it's less than a 10% improvement is my general recommendation, especially if it's a lot of code or it makes the code more complicated. So there's two ways of getting benchmarks out of code. One is to use a tracing profiler. And the way a tracing profiler works is it starts a trace before it runs the code, and then it runs the trace after it runs the code. So this adds an overhead, but it's very, very accurate. Another way is to do sampling, where you run the code, and then whilst the code is running, a separate process will ask Python what it's currently doing, basically on an interval. So let's say 60 times per minute, it will ask Python, what are you currently doing? And then it will record those as samples, and you can get those samples as a view to see on average what the process spent most of its time doing. So these are the two types of profilers you can use, and you can use both of them to make benchmarks. When you're selecting a profiling tool, I grouped them into these two categories, which is a tracing profiler and a sampling profiler. Samplers basically has less overhead. So with a sampler, it doesn't make the code run slower, but it's less accurate. So a tracer will be more accurate, so it'll give you more accurate times and tell you which functions are run and how many times, but it will make the code run slower. So you definitely don't want to introduce a tracing sampler in a production environment. And also you might find that if you add a tracer in a large or complex application, it actually makes it so slow that it's unusable. So here's a series of options. You probably also want to consider which versions of Python they support and whether they support multiprocessing and async. This is an example of a micro profiler, which uses sampling. The library is called Scalene, and the output of Scalene would be this kind of output. And you can see line by line how much time was spent by the CPU, how much memory was spent, and where the majority of the time is spent on each function. This is a really detailed view. If you have a particular function or an algorithm that is very hot, that is, it runs lots and lots of times, and you want to optimize it, then this can be a really good view to look at the specific detail. And I'll give one example after we go through this. So there are some other things you can do. I have a package called perflint. It's a PyLint extension that highlights some of the rules that I'm going to go through today. These are quite specific, and they're just general optimizations you can make to Python code. One of these is something called loop invariance. In other languages, so in C and C++, the compiler does this for you. In Python, it doesn't. So in this statement, I've got two functions that essentially do the same thing. In the first function called before, I'm using an expression which is the length of x multiplied by I, but neither x nor I change in the loop. So that is something called an invariant statement. That is, it always evaluates to the same result for every iteration of the loop. The perflint tool that I mentioned would highlight this for you and tell you that it is invariant. But it's important to note that Python would not do an optimization that a language like C++ or Rust would do, where it would actually move the statement outside of the loop. So in the second example, that is 55% faster. It is more code and it's probably less readable, but it is an optimization you can make by moving the expression outside of the loop. Another example is that comprehensions are much more efficient than putting things into for loops. So for example, if you were to do this A and B, the B statement runs 23% faster in Python 3.11 because comprehensions, dictionary, set, and list comprehensions are all much faster in Python. So this is an example of where the linter would identify some areas where you should have used a comprehension and give you the feedback in the code. Another thing that I noticed when I was looking at the NES emulator was that the developer used the wrong data structure or a data structure that was probably inefficient. So I've developed this decision tree where you can pick whether you need to use a set, a list, a byte array, a string, a frozen set, or a tuple, depending on the needs of the container. So mutability is obviously very important. If you don't need a mutable type, so it can be a tuple or a string, and then you tend to get a lot more efficiency when reading or indexing from that type. Another consideration is picking between class, data class, a dictionary, or a name tuple. So there are some decisions that you can make, and one of these is actually the performance of the types. So data classes are very convenient. If you've ever used the data classes from Python 3.7, they're a really convenient type, and they make the code simple and easy to read. So in this example, I've got a class called pet, which I've made a data class. It has a number of legs and the noise that it makes. I could also represent that as a name tuple, or I could have a pet and then using the typing.name tuple base class. This is 3 ways of achieving the same thing. Or a fourth way is that I could introduce a class and add all the parameters myself and implement the repr method. So this is probably more code, but it's 51% faster than data class. It's 28% faster than a name tuple, but it is more code and it's probably less readable. So I'd say that this is an extreme measure, but it can be very effective if you profile code and you've noticed that a lot of time is spent in data class magic methods. Data classes are very nice to use and they're very convenient, but they are very slow. This is a benchmark I did on Python 3.9, and you can see a comparison of the execution time to create the class and to read the attributes. The slowest type that you could use is a data class, and the fastest type that you could use is a hard-coded class using slots. Another thing that's important is that Python has a concept of iterables, and I often see people casting an iterable into a list. So this is eagerly iterating it. So if they don't realize that you can use iterators, then you might find some cases where people in the code base have wrapped a list statement around an iterable to use it in a for loop. So the linter I mentioned earlier on would pick that up for you and highlight it. Another thing which you will find in micro optimizations is there's a concept called dry, which is don't repeat yourself. This is a general design. It's part of the solid principles. However, in Python, calling functions has a significant overhead. This is different to C and C++, and it's very different to languages which have an inline operator. Python does not have such a concept of inlining. It does for list comprehensions in Python 3.12, but for everything else, calling a function in Python is very expensive. So something that I found with the NES emulator when I read the code was that the developer had made lots of one-line Python functions that were called millions of times. This makes the code really readable and easy to understand, but it made it incredibly slow. So at the moment in Python, if you have lots of one-line functions, this can be a massive cause of slowdown in your code base. So, for example, if you had, this is a bit of a exaggerated example, but if you made a function to add two numbers together, and you compared that with just making the statements by hand, it would be 65% faster. Okay, so there are four things that I've highlighted here. One is loop invariant statements. The second is to utilize comprehensions where possible. The third is to select the right data structures. And the fourth is to avoid small utility functions in hot areas of code. Utility functions are fine if they're not called very often. If they're in a tight loop, that is a loop which runs hundreds, thousands, or millions of times, then try to avoid calling out to functions as much as possible. This would also apply to methods and class methods. So if you've done some profiling and you found a particular block of code that you think you need to optimize, then I would say to look at following these four constructs and to sample and baseline, and then track any changes and regressions. The optimizations that the Python team are doing on CPython itself roughly follow some of these constructs, but they're also looking at changing the algorithms. And then if you can introduce profiling in your build workflow, this can be a really effective way to catch issues in code review and to avoid performance regressions. Okay, so far we've looked at some specific Python design considerations. I'm going to spend the rest of the talk talking about load testing, which is looking at the whole system and to test the performance of a running application or a running system. So I've got two analogies for the concept of load testing. One of them is that you might consider football or soccer, this is called in some countries, as a load testing problem. And the reason is that in the World Cup in particular, some of the games are watched by a huge number of people. And what the electricity providers have to do in Australia, in the UK, probably in Korea and Japan as well, is they have to predict how much demand will be put on the system, how much electricity will be put on the system at particular times. And an example that I'll use is because I'm English, in the England versus Italy game in 2020, 1.1 million people made a cup of tea at the same time. This created a 600 megawatt load on the electrical grid in the UK. And because they all made a cup of tea at half time during the game, they did it all more or less at the same time. This was in effect a load testing problem because you had a number of users, you had an amount of load, you had a ramp up time, and the designers and operators of the electricity grid had to figure out in advance how they would cope with this demand. When it comes to applications, it is very similar. Something else, this is a TV show in the UK, and I was asked to help to load test it. That's not a real person, that's an actor, but it was a drama on TV in the UK, and the people who made the TV show said that at the end of the episode they would say that you had to solve the murder, and everybody had to go onto the website at the end of the program to try and solve the murder. And the operators of the TV program asked me if I could help them to predict how many users would go onto the website and then to test whether or not it would work. So this is basically some of my learnings from that exercise, and how you would think about designing a load test. So there are basically two variables with load test. The first one is the number of requests. And if you think of this as a queue of people, so one at a time, if you had 10,000 requests and a concurrency of 1, so you let in one person at a time, you would create a very large queue. A concurrency problem is where you have a lot of people. So the concurrency is basically the number of simultaneous users. A concurrency test would be something like this, where you've got a lot of people trying to leave a stadium all at the same time. So if you put them through let's say a queue that could only fit 10 people in it, you would have a huge bottleneck. So when you're working with load testing tools, you will look at the number of requests and the amount of concurrency that you want. A common mistake that I see people make is they would use a tool such as Apache Bench to run a load test. Apache Bench you can run on the command line. It's a very good tool for testing web servers. It's not a good tool for testing load testing applications. So in this one, I've run Apache Bench with N, which is the number of requests of 10,000, and a concurrency, which is C of 100. The reason this is not a good test is because it doesn't simulate how users actually use applications. It is basically sending 100 requests all at the same time, and then as soon as each one finishes, it sends another batch of requests. This is not actually how users use applications. This, I think, is more realistic. This is a screenshot of a game called City Skylines. If you've ever played this game, you probably recognize the problem that I have in my city. And this is actually more realistic of how an application works. In this game, you have to solve basically a population problem where you have trapped cars driving around, taking people to different places. This is similar to how applications work because users go on different paths. People go to different parts of the application, they click on different things, and they also take time. So there's a variance of where they go, the path they take, and the time that they take. And in reality, there's actually a lot of randomness to user load. So in this example, this could be 30 requests a second going to the home page, 15 requests a second going to the listings page, and 5 people a second going to the search page. So that could kind of visualize your cars. But we can see we've got a bottleneck here, which could be our database. And you wouldn't recognize that unless you try to vary your inputs and vary the code paths. So not all users have the same connection. Not all users arrive at once, unless it's a halftime cup of tea, where you can kind of predict what time everybody will go on the website. The users take different journeys, and also users wait between clicks, whether that's an API or a web app. So what you can do is, first of all, when you're designing a load test, you need to understand the user flows. So users take different paths through a website or an application. The paths are probabilistic, so you can use analysis to understand what percentage of people go on which path. So if you can start off by using any tool, you can do this in application insights, where you can see user flows and the percentage of users that go to different parts of the application. But this is a good way of visualizing what the users are and then grouping them into personas. And I'll show you one persona in the demo in the load test. Another really important consideration is that when you're designing load tests, you need to randomize the load put on the application, because users are random. They will read things, they will click at things, and they will take their time. So for example, if you were generating a real load for a load test, you could have a first user who went to the home page, waited for a few seconds, went to the search page, they looked maybe at the second page, and then they clicked on a specific product. A second user might do something different. And then the third user might do something completely different as well. So when you're creating load tests, you want to try and randomize the time and the separation of the tasks as much as possible. I also highlighted some of these in blue because in most apps and in most web applications nowadays, there is a lot of JavaScript involved in a UI and an interface. And JavaScript tends to put an additional load on the application that you can't necessarily see if you just test the API. So for example, I've seen this before where customers have built an application and they've done a load test just looking at the server load. And then when they've launched the application, it hasn't been able to cope with the load because most users have left their browsers open and they have some sort of AJAX code which is polling and updating a table or a view every few seconds. So they didn't predict that a user wouldn't just click on a page, that they would actually make another request every minute because they'd configured their JavaScript to refresh the contents of a page or to refresh the status. So it's really important to take that into consideration when you're designing the test. There's a tool that I recommend you start off with to do your first load testing, and I will give you a demo of this in a minute. This is called Locust. It's a free and open source tool. It's written in Python, and you write your load tests in Python. So you can install Locust manually on your local environment. You can also run it in a server in the cloud if you want. It's important to note that when you're running it locally, if you're also running the application locally, so you're running everything on your machine, you can skew the results because Locust itself, uses CPU. So ideally, you'd run the load test and the application on different environments, but you can run the whole thing on your machine if you just want to do testing and development. Okay, so this is what the most simple test would look like in Locust. So you write this in Python, you write a class called a user class, and you inherit from HTTP user. And then you implement functions and you wrap them with a task decorator. There's also an attribute for each user, which is the wait time, that says to randomize the time between each task, between two numbers. So here I've put this as 3 and 5. So this means that each user would wait between 3 to 5 seconds between each task. You'll also notice that the first task, the index task, has a 3 in parentheses. This means that this happens 3 times more than the other tasks. So a user is probably 3 times more likely to go to the home page than they are to the destinations page or to a specific index. Okay, so I'm going to show you a demo of Locust, which is here. Okay, so I have an application. It's a very simple application. It's written in Fast API, and it essentially is an application that is a to-do list. So I've got some routes in this application, and I have it running in my browser. Where is it? Okay, here it is. Another one. Okay, this is the API that's running. So I can see I've got the different methods. I can look at the lists. I can create a list. And there's also a front end for this application, which is running and it's completely JavaScript. So this is the front end that I've created. And I wanted to design a simple load test for this environment. So what I've done is I've looked at what steps do I think a user would take, and then written a simple load test for Locust. So this looks like a user class, like I mentioned before. And I've created one task, but that task has multiple steps. So before I ran this test, because this environment, this application has just been deployed, it didn't have any data in it. And something which I'll mention later is that when you're designing load tests, you really need to consider what data is in the application. Because if you test an environment that only has one test user or 10 test users, then the application is going to perform differently than one that has 10,000 or 10 million users. It sounds obvious, but I see people make this mistake so many times when they're running the load test of an environment in an isolated environment. So what I've done here is I've made a seed script where I created some test data for my application in the container so that I know that it always has data in it before I run the test. And then in Locust, I've created a simple task where I go to get the lists. I look at all of the to-do lists, and then I pick one in particular. And then I've randomized getting one or more items from the list. So these are my steps, and this is the task that I have. So where was I? So once you've installed Locust, you run it from the command line, and it will start a web server. Okay, so it will ask you a few questions. There must be a dark mode. Here we are. So it will ask you how many users you want at peak concurrency. So let's say I want 100 users. It will ask you how many users to start per second. This is really important because you'll find in load tests that if you make this number too high, you'll actually create a bottleneck in the application that's not realistic of what users are doing. So I'm going to put 5 in there. And then you need to say which environment you want to test, which is this one that I've deployed. And then you can say how long you want the test to run for. So once I've done that, it's going to go and start to create the tasks and to start issuing the requests to the application. So I'm going to see this table here. And then if I go to charts, I'm going to see something a bit more meaningful. So this first table is the number of requests per second that it's issuing. And as it ramps up the number of users to 100, that number is going to keep going up. Then I'm going to look here to see the response times on average for the application. And I want to see a stable line. If I try and start too many users too quickly, then you'll probably see a bottleneck. And a bottleneck means that this line is unstable, so it keeps ramping upwards. And I can see the number of users that are running here. Another cool thing about Locust is once it's running, you can actually up the number of users. So if you're happy that the application is stable and the performance is stable, then you can increase the number of users at any point. Okay, now so far I've just showed you how to load test the API. Now there's a couple of reasons why this approach is quite limited. First of all, I'm only simulating a server request. I'm not actually simulating everything that can be done on the whole application. So the other tool I wanted to highlight is something called Playwright. In that test, I was making server requests to the API, but this application has a UI as well. And you can see in the UI, I can click around, and it does make API requests, but those are going to look quite different. And you'll actually find that for one page load, like if I look at this specific list, that could have issued 10 or hundreds of network requests. So if I'm only testing the API endpoints, I'm not really simulating what a user would do. This can be useful if you've got a mobile app and you want to simulate API loads specifically. But if you want to simulate real users, then you want to simulate them through the interface. You can do this by trying to capture what requests to the server the user would make. But in some applications, this is really difficult to achieve. So what I want to show you instead is another tool, which if I stop that load test, because there we go. Let me just stop that. Okay. I'll show you another tool, which is Playwright. And Playwright can be used with an inspector. Okay, so if you install Playwright through pip, and then you run Playwright code gen, then it will open up a browser, this browser here, and it will open up a code window. So what you can do in here is, let me see if I got a reset button. I'll just close it and start again. Okay, so Playwright's going to open up a browser. This is actually a special browser because it's in a recorder. So whatever I do in the browser, it's going to turn that into code. And you can specify what you want that to look like. This is really good if you want to write tests for PyTest, for example. You can say, I want PyTest, and it will create tests for what you've done. So if I click through on the application, change some text to type it in, and then save it, it's going to create all of those steps as code. What you can do with Locust is you can pick library async. You can copy that code and save it as a file. And then you can create a load test that says, run this script for a user. What that will do is actually run a browser in the background, and each user is actually a browser. So it will fully simulate the whole application. That's different to running it by just making server requests. Okay. Something else that's important is if you're emulating server requests, you often find that you have security controls. So you might need to patch CSRF data. This is in the slides if you need this particular code sample. Like I mentioned before, common mistake is to load test an empty application. So I recommend that whenever you do a load test, even if it's in development environment, you try to seed that development environment with as much fake data as possible, or as much fake data as is realistic. There's a library called Mimesis, which has a huge database of names, addresses, passwords, and you can use Mimesis to generate realistic looking data and to put that into a test database for a load test. So trivia, what's the fastest implementation of the Fibonacci sequence for an input of 15? And the answer would be to just return a hard-coded value. I'm making this point because when it comes to applications in Python, often one of the quickest fixes to performance problems is to cache things. So there are so many caches available to you. You can put a cache at the front end in the form of a CDN or a reverse proxy. You can cache Django at the middleware level. Flask and FastAPI are very similar. You can cache templates. You can cache queries in the database backend. You can cache objects using something like Redis. Or you can put LRU caches in Django as well. This is specific to Django. You can do similar things with FastAPI. Mostly you'll find, and I'm sure in applications like such as yours, you have so many users, you're pretty familiar with caching techniques. But it is important when you're doing load tests to think about caching, because if you hard code in your load test the user or the path that they are taking, then the cache will kick in, and you often end up just testing the cached version of the application. So it's important to try and randomize in your tests by looking at or randomizing the inputs or randomizing the path that you're taking. I think that's super important because otherwise you won't just get a really positive load test because you've only been testing cached pages. So when you're looking at the Locust results, a lot of the time you'll see a graph like this at the top and a table like this at the bottom. The initial peak is what I call the warm-up phase, and that is when often most of the caches kick in, but you'll see a jump in response times. It depends on how many users you're seeding and what ramp-up time you have, but the most important line you're looking at is the stable line. So does it look flat or does it keep increasing? And then when you're looking at the percentiles, there are two you can look at, the 90th percentile and the 99th. Another consideration is to look at the 95th. My recommendation is to look at the 90th or the 95th percentile. That means for 90% of users, what response time would they have? Something like 300 milliseconds, it depends on the application, would be fairly acceptable. But you'll see in the 99th percentile, I have 2.3 seconds. That's actually skewed because of the warm-up time, which is why we try and exclude those from the metrics. You also see in this second graph that as I increased to past 190 users, it went from a flat line in the response times to a line that was trending upward. This shows me that that is a bottleneck in terms of the number of users that either the application can handle or there's something else that's causing a queue or a problem. So I'm going to show you one more thing, which is the application that I had been load testing. Okay. So the application that I had some telemetry in that application as well. So I didn't show you on the code, I'll just show you now. This is a fast API application, and I've also installed OpenTelemetry into it. This is useful for me because when I'm looking at the load test results, I saw this graph, which is the request per second, and I saw the response times, which were fluctuating, and then I had this big peak here. So for some reason, the response times jumped up towards the end of the test and then came back down again. I don't really know why, but I was capturing the data on the back end and pushing that information up into OpenTelemetry. OpenTelemetry can be captured in any number of ways. I'm using Azure Monitor, but that means I can capture this time span when the test was running, and I can see a distribution of the response times here. This is OpenTelemetry is an open standard. It's an open source tool. And if I click on, so for example, the slowest in the 99th percentile, if I look at those particular samples, then I can drill into those. I can see those with delete requests. And I can pick on any one of those and see how long did it take and then what was it doing at that point. Something else you can do when I was running Locust, in this case, I'm running it with 100 users. That's suitable probably for my machine and my environment. But I would recommend also looking at running multiple users in multiple environments if you want to simulate something that's in the tens of thousands or above. I did run this particular load test in a different environment. So I was running it with 5 servers running Locust all at the same time to issue 43,000 requests over a couple of minutes. And you can use that basically to try and scale out your testing environment. Locust has got the ability to do this, and we've got the ability to do this in Azure load testing as well. But there's definitely other ways of doing it. So that really wraps up my talk and what I wanted to share. And I'm sure many of you got some questions as well for me in the chat. So I will stop sharing my screen.